Okay, so we're trying to figure out whether if it doesn't have a central atom, how do you tell if it doesn't have a central atom, if it's polar or pure? Okay, if it's a regular old molecule and it has a central atom, then basically you look at if it has the unshared pair on the central atom, or if there are bonding atoms that are different. But if there is no central atom, then what we're going to do is we're going to be using what we call electronegativity. So polar and pure, nonpolar, polar and pure covalent bonds. And when we talk about bonds, this is going to be between two atoms. And that means no central atom. So if we don't have a central atom, if you don't have a central atom, then this is what you're going to do with just two atoms. All right, so electronegativity. Remember electronegativity, electron affinity? In 4 words, how would you define electronegativity?
Negative.
Something is negative? It's the same thing as electron affinity. Remember that? Want for additional electrons. Want for additional electrons. We're going to change it up, though, a little bit. All right? So instead of saying additional, electronegativity is the want for shared electrons. Okay? So it's the same thing. They want additional electrons, but this time the electrons are going to be shared. So in a covalent bond, they're sharing, and like we talked yesterday, how if you have two siblings and there's an iPad between them, that it's supposed to be shared, but it's never really shared equally. So same thing. If I have two atoms and they have different electronegativities, one of those atoms are going to be pulling on it stronger than the other. Am I right? And so we get something that's polar. And again, polar means, in 4 words, having opposite ends. You did it in 3 words. All right, so having opposite ends. And so if I have 2 atoms, all right, and they have different electronegativities, they're going to have opposite ends because one's pulling stronger. Now, according to the periodic table, which element on the periodic table have the strongest electron affinity or electronegativity? Who really, really wants the electron the most? Fluorine. So fluorine really, really wants the electron the most. So any element that's near fluorine is going to want that electron the most. All right? So how do we tell what the electronegativity is? If you take your paper and you flip it around on the other side, you'll notice a chart of electronegativities. So find the electronegativity for carbon. What is the electronegativity of carbon? 2.6. And chlorine, what's the electronegativity of chlorine? 3.2. So obviously here we have an imbalance. They're different. One is pulling stronger than the other. Who's pulling stronger? Chlorine. And so think of it as a tug of war. You got a tug of war. We got chlorine and carbon both pulling on the electron, and the electron is going to be more towards chlorine. And so do you think these electrons are going to be shared equally or unequally? This is going to be an unequal sharing. So carbon and chlorine, here's their bond. If I had carbon and chlorine, they're sharing this electron will spend more time around chlorine than carbon. So the electron cloud would look a little lopsided. Okay? So the electron cloud would look a little lopsided and be more towards chlorine than carbon. All right? Now, we said that this is going to be, it's going to have opposite ends. It's going to be polar. But can you tell by the picture which side would most likely be negative? Would it be the carbon side or the chlorine side? Why the chlorine side? The electrons will spend more time there, right? And so this will be the negative side. Now, we're going to label this as negative. Now, pay attention to how I'm drawing this. Do you see how I made an S and I closed the bottom up? That's sigma. Yeah. Yeah. No. This is lowercase sigma. Lowercase sigma. You're thinking of capital sigma. All right, lowercase sigma. This would be this sigma negative. Now, we're going to use sigma because sigma means partially. It's a partial charge. This is going to be partially negative. All right? Now, partially negative, because the electron is not fully leaving the other atom. All right? It's just being pulled directly towards chlorine. So it's not quite leaving. If it left, then it'd be a -1, right? So it's less than 1. It's partially negative. So we're saying that this end, all right, the electron basically spends more time here. And that's what's making it partially negative. Now, on the other side, since the electron is not there all the time, this is going to be partially positive. Okay? So which side do you think is going to be, so if it has highest electronegativity, if something has a higher electronegativity, is it going to be partially positive or partially negative?
Negative.
Partially negative. So electronegative, the higher it is, it's going to be partially negative. So does anyone have any questions on that? Can you label the atom that's going to be partially negative and partially positive, and can you explain what partiality means? All right. And then the lowest electronegativity is going to be partially positive. All right. Would you say this is pure or polar? This is definitely polar. All right. Any questions on if they have two different electronegativities? All right. If they have the same electronegativity, let's look at H and H. So can anyone look on the other side and tell me the electronegativity of hydrogen? It's what now? Just straight up 2? 1 point? 2.2. And what's the electronegativity of other hydrogen? 2.2. Right. So the electronegativity is going to be the same. So what does that mean about the electron that's being pulled on in the middle? It's going to be equally shared. So this is at times we're going to have something that's equally shared. Right? So what does the electron cloud look like? If I have hydrogen here, here's the bond, here's another hydrogen. Okay? Yeah, as best as you can. As best as you can. Let's see, we're going to make an electric cloud. That's somewhat equal. Okay? So is there going to be a positive and negative end? No. And so what would you call this bond? Pure. Pure. Okay? All right. Any questions on if they have the same electronegativity and how does it make a pure bond? All right. Now, ionic bonds. Are electrons shared in ionic bonds? No, they are not shared. So, ionic bonds are not shared. So, can they be polar or pure? No. So, they cannot be polar or pure because there's no sharing done. All right, so right down here, you'll see the range of difference. So if I took two elements and I subtracted them, if the difference is between 0.0 and 0.4, they're pretty much close enough that we can say that they are pure covalent. Okay? They are pure covalent. And if I have 0.5 to 1.6, this is going to be what we call polar covalent. But what if the element is pulling on it so strong, it just rips it off the other one? What's that called? So one element is just going to lose its electron, and the other element just gains its electron. Ionic. It's called ionic. And that's what happens when the electronegativity is 1.7 and above. That difference is so great that the electron will be ripped off the other one. It's not shared. Yeah, it's not shared. One's pulling out too strongly. And so we got an ionic compound. Okay? Any questions on that? All right. So if you go onto the back side, again, with your chart, and any time you need to look up electronegativities, here you go. This is your electronegativity chart. Okay? So you can look it up here. Now, if we look at arsenic, what's the electronegativity of arsenic? 2.2. And sulfur, what's the electronegativity of sulfur? 2.6. So the difference is going to be 0.4. So we got a difference of 0.4. Oh, right. So if it's a difference of 0.4, according to our chart on the other side, yeah, very good. Pure covalent. Almost bordering on polar, but pure covalent no matter what. Okay? All right. We're going to skip number 2. That's not really for our purposes. All right. So why don't you go ahead and do the rest of them 3 through 10.